I'm very happy to be here today, and I'm more than excited to be on the first virtual meeting like this, our seminar and our discussion panel regarding brazing technology. My name is Adam Adamek, and I will be the host for our discussion about brazing. What we can say? We have different methods of joining materials together. We have gluing, we have fastening, we have welding. But brazing, it's a technology very well known from thousands of years, but we have still many issues to solve. And please remember that why we are here today. We are here to share our experience, our knowledge, and between us and between you. And I hope you will be happy. And if you have any comments or additional questions, please also use a chat window and please type your comments or questions. We will be happy to have such interaction with you. We have a great team of our experts. And who is expert in internet? And I found a nice explanation according to Niels Bohr that the expert is the person who made all possible mistakes in a very narrow field. It's a little bit discussive for me, so I would like to present you my personal way of the expert, which is a person who have some experience, have a knowledge, but is able to share this knowledge and experience between different people. And that a true expert for me is a person that I can call and always have an answer. So this is, please remember about this when we speak for a moment with our experts. So who will be in our discussion today? First person is graduated at Academy of Mining and Metallurgy in Kraków, Poland. PhD degree in exploitation and mechanical engineering at Warsaw University of Technology. Today is responsible for strategy of special processes development with 20 years of practical experience. Ladies and gentlemen, please welcome Irena Dul. Hello, Irena.
Hi, Adam, and hi, everybody. Hi.
Hello, nice to see you today. And let's invite the second person. The second person graduated at the University of British Columbia, Vancouver in Canada. PhD degree at Academy of Mining and Metallurgy in Kraków, second time the same university. At Valeo was the key person for introduction of aluminium brazing. Then brazing expert in Visteon company in Great Britain, technical service manager at Solvay, and today's consultant in aluminium brazing. So, ladies and gentlemen, please welcome Leszek Orman. Hello, Leszek. Good to see you.
Hello.
Hi.
Nice to see you. Nice to talk to you.
To combine, yes.
One small remark about the definition of Niels Bohr.
Please do.
I think that there is something in it because I've made many mistakes in my professional life. It's perhaps not every possible, but many.
I agree, and from my point of view, always, if we made a mistake, it's the best lesson for the future. So let's keep it in this way. Thank you, Leszek. And to combine a great team in complete, please, the third person in our discussion graduated at Academy of Mining and Metallurgy in Kraków again. And brazing experience started at Listeman, then joined the Warsaw Institute of Aviation, and then General Electric Company for brazing applied on gas turbine repair. So it was quite on the beginning of our commitment. It was a little bit strange for me how to braze and repair the blades, but then now I have more information about this. And today is a global brazing engineer at Danfoss company. So, ladies and gentlemen, please welcome Adam Gaik. Hello,
Hi.
Adam.
It's very nice to be here, and
good.
The pleasure is mine, I think. Yeah.
Great to see you all. So now it's time to start our technical discussion. With the first question, we have already discussed, and to our attendees, please also remember that we already discussed something. So some of questions are partially prepared, some of them are surprising. And let's start with the first question, because I believe we have some guests which are the beginners in technology of brazing, some of guests which are real experts, and it's always discussive. And if we can say something about the definition of brazing, what it is, how to explain this to the engineers. So Leszek, if you can start to say something about this, please. How do you see this aspect?
Thank you. Well, brazing is a process where we join metals using a molten filler metal. And on melting, the filler metal spreads between the closely fitted surfaces. And during that process, there are some metallurgical phenomenon taking place. One of the most important is diffusion between the base metal and the filler metal. Diffusion means that some of the atoms from the base metal go into the filler metal and vice versa. Some of the filler alloy atoms goes into the base metal. And upon cooling, a metallurgical bond is formed. And the very important point about definition of brazing. The filler metal melting temperature must be below the melting range of the metals to be joined.
Exactly. If we do it right.
Term often used is soldering. Soldering basically it is the same as brazing, but performed at temperature below 450 centigrades. And the third process where we use molten metal to join elements is called welding. It is joining of metals using a molten filler metal. And in this process, the welded parts are also partially melted. That's just the main difference between welding and brazing. In welding, the parts are also partially molten.
If you remember,
and
when
the molten filler mixed with molten metal of the joint parts forms the joint upon freezing.
If you remember,
and I guess I show you a very short movie in the so-called glass furnace, which would visualize the process of brazing, of furnace brazing, because normally we cannot see it because it is inside a big furnace.
Before I present this movie, if you remember our pre-discussion before this discussion panel, Irena mentioned that the critical issue is always to remember that the brazing is a metallurgical bond. Am I right, Irena?
Yes, exactly.
It was good to remember. But before this discussion, I received a nice movie from Leszek. So let me show you the movie. And Leszek, if you can explain what we see on the movie right now.
Okay. In this movie, we are going to show how two elements are brazed. Small coupon, square-like, 20 millimeters by 20, with an angle. And for that process, we must also use flux, because flux is a factor which cleans the surface, which prepares the surface for the filler metal to flow freely. Here you could see how the flux slurry is drying on the surface of the part. It is a real-time movie, and the coupon is put on the top of the furnace, so you can see how it dries.
It's laboratory condition right
yes,
now.
It is a laboratory furnace. Flux is a substance which looks like white powder. When it's dry, it covers the surface here quite uniformly. And then we put the angle on top of it and a small piece of filler alloy. We put the whole assembly inside the furnace. We set the temperature, which in case of aluminium is 600 centigrades, and we run nitrogen through the furnace. It is important to have inert atmosphere inside. Now the flux has melted and it started preparing the surface. Now the filler alloy melts and it flows, it forms a joint. It is the same in the slow motion.
I must tell
Flux
you,
is being open.
I must tell you, when I first time saw this movie, I was really surprised how fast it is.
And the filler,
flow.
Filler fills the joint. Please note that there is now the movie is stopped, but that's okay. On the upper side of the angle, we can see that there is a shadow. And this shadow, it is how flux spreads on the surface, even against gravity. And this is the key factor for success of brazing. Flux must prepare, must clean the surface, must remove the oxide from the surface. And I will,
I don't know, Leszek, thank you very much for this explanation. And what I wanted to say is that when I saw first time this movie, I was extremely surprised how fast the capillary force keep the brazing alloy inside the gap. And this is additional question to everyone. Do you have any idea what is the speed of brazing alloy when brazing occur? Do we have any approximation?
I never measure it.
But even on this movie, it was.
I don't think that we know something about it. Well, it is fast, but the real speed of brazing is actually determined by the speed of flux spreading, and that one is not so fast.
Yeah, I think maybe it's also determined by the thickness of our gap. But let's continue our discussion.
Correct.
Irena, Adam, have you seen anything like this before during your brazing experience?
Yes.
Yes.
Maybe not exactly this movie, but I saw this during the process. Some of the processes are not done in the furnace. That you can see them outside, like here. So.
Yeah, induction brazing. The space is open, and you can see such phenomena.
Yeah, it's good you mentioned about induction, because it was already explained about even laboratory about the brazing furnace. But you mentioned about induction. We have different methods of brazing. And when I said about technology which is known from thousands of years, we can find some nice jewelry made in brazing way even in Egypt museum and so on. But if we can say something more about different methods of brazing, if you can divide it in some way, Adam, can you do a favor and explain it to us?
Yes, so the brazing is very versatile and broad technology, and you can divide it in many ways. What I did then is I divided by the heating methods. What kind of heating methods we use to heat up the parts and to join them. So one of the oldest and the basic methods is the torch brazing, where we can have a different fuels to burn the torch. And it's pretty versatile technology, manual, but it requires a lot of skill from operator to use this technology. It's like a little bit like a TIG welding, but maybe a little bit easier than TIG welding, but it requires the skill and experience to use this technology.
But can it be automated also?
Yes, and there is a lot of automated machines using this torch brazing. Another package is a furnace brazing, because we can have vacuum furnaces and continuous belt furnaces. They are a little bit different how they operate. Both of these types of furnaces using some kind of protective atmospheres. In vacuum furnace, we have much more cleaner atmospheres because we can use vacuum or gases like nitrogen, hydrogen, argon. I forgot about the argon here. But you're starting with a vacuum at the beginning. So the atmospheres you introduce in the vacuum furnace are much more cleaner. On continuous furnace, we can have the endothermic, exothermic atmospheres and dissociated ammonia and nitrogen based. Mostly these atmospheres are nitrogen hydrogen based, and some of these atmospheres are not very good for some of the materials. And but that kind of furnace can produce a lot of products per hour, I would say.
In one batch.
And then we have the induction brazing, which is very specific because we're using the electromagnetic field that it's creating eddy currents in the parts, and we can use the induction brazing to braze metallic parts. But that's pretty straightforward. And induction is also very fast process. For example, we can braze the parts in 10 seconds or even less compared to the torch brazing or the furnace brazing. And you can combine it with the different protective atmospheres. You can use a flux with it, or you can do it without the flux. You can control the process a little bit better. But it's it has some drawbacks, like for induction is very localized heating, so you can the joint is never heated as uniformly like in the furnaces. And the same situation we have with the torch brazing, where we locally heat the parts, and of course you can heat a little bit wider space with the torch and with the induction, but that will require a different tool or technique. With the furnace, you heat up the whole part, and the heating is very uniform, and heat distribution, which is quite important for brazing.
As you may expect, I am a big fan of furnace brazing, and it's sometimes it's a benefit, sometimes it's a disadvantage of heating the complete component together, not only the brazing place, but the complete element. But have you seen any of components that is, let's say, for the one component, but it's possible to braze in torch brazing, furnace, and induction, and without any issue? Have you seen something like this, or you don't have any example?
I mean, yeah, some in my current company where we're producing the valves, some of the valves could be done in all of these methods. It depends on the size and volume that we want to process. So it could be done with the induction, torch, and in the vacuum furnace. Not all of that. It depends on the base material that we are joining, but you could use all of them on some of the products.
I'm asking because,
of course,
I would.
Yeah, please, Irena.
I would like to also add that the problematic may be induction brazing, because sometimes the design of the coil to heat material may be a little bit complicated, and sometimes furnace brazing is easier for such application to avoid a very complicated coil.
What do you think, Adam? Do you agree?
I just heard it partially. I didn't hear it whole the sentence. So,
Adam, I don't hear you.
Yes, that was the problem.
We will
Adam,
try to improve our connection. Irena, please repeat only to Adam. What did you say?
Yeah, I said that sometimes problematic is design of the coil for heating during the induction brazing. And in such application, when we have complicated shape, sometimes it's better furnace brazing than design very expensive and complicated coil.
So there is a solution there is a solution for complicated coils that started like 2 years ago. Now we have ability to 3D print the coils in the copper, because some of this technology is growing. I mean, the 3D printing, and since we are able to print in a copper using the copper powder, we can create very complicated coils with very complicated cooling channels inside. And the cost is very low comparing to the traditional coils manufacturing methods.
This is always according to my experience. I agree that if we have already the component which is already designed and manufactured, it's really hard to find, or sometimes the furnace brazing is the only opportunity to make a proper connection of the several or hundreds or sometimes thousands of joints inside one element. This is, from my point of view, is the biggest difference between furnace brazing and torch or induction brazing, when we do mostly one element after another with one brazing connection. Irena, you mentioned something. Yes. Please, Adam.
I mean, it is, as you said, that the furnace is used for bigger volume, and torch induction is for less volume and for something that we want to join a couple of times.
Yes, thank you. And what was interesting to me, it was something explained by Irena, that the design has to be changed or prepared, especially to the different brazing method. And according to my experience, it's a really great challenge to have the ready produced part and then to start to do brazing. And many times I see a lot of different point of views between designer of the components and then the people that has to braze these components. And if you can say something, why brazing instead of welding? Which technology is for what kind of applications? Irena, it's your turn. So please share some of your experience with us.
Yeah, in my point of view, there is no issue which process is better, brazing or welding. The question is which process is better for application we have. Sometimes design of the joint makes impossible welding operation. In case of welding, a good access for manipulating welding torch, electrode, and we need also very good view of welded area. And generally, more access is needed for welding operation. So in case of limited space, brazing is easier to perform and is chosen more often than welding. So the design of the joint and limited space is better sometimes for brazing than for welding. The next issue is that the better result of joining thin elements we can achieve during the brazing. Welding is high energy process. The base metal must be melted during the process. And in case of thin elements, the burns can occur, what results a hole, the craters in the weld bed. So when we weld thin parts, also the skills of the welders are very, very critical. The same as for fuel, for torch brazing. This is manual, very often manual operation, and the skills of the personnel doing this process is critical. Generally, for the thin parts, as you see at the left side of the picture, there is brazed joint. You can see that it's very, very smooth, very thin, and the quality is very good. The next slide, please. The next advantage of the brazing is possibility of joining different materials. Welding process is dedicated only for metals. Using brazing process, we can join metal with ceramics, for example. Of course, we have to use special type of brazing filler metals, active brazing filler metals, but in that case, we can join completely different materials with completely different properties and different coefficient of thermal expansion. And the last issue is the economy aspects. Brazing processes are generally a little bit cheaper than welding. Especially in case of furnace brazing, we are able to do 100 joints in the same time, in the same operation. And the brazing process can be also combined with heat treatment. We call that this is the concurrent heat treatment.
In
of
parallel,
course,
yes, why?
Not near parallel, exactly. As I show in that one segment is brazing, the second is concurrent heat treatment. Of course, not every brazed joint requires heat treatment. It depends on the role of this joint, what mechanical properties of the base metal, etc. But in aviation, in the industry that I represent, such processing like heat treatment of the brazing joint is necessary. We do it for all parts we brazed. Due to the fact that only one heating and one cooling segment is done during this concurrent brazing and heat treatment cycle, we have also less distortion. And in general, the brazing process doesn't require as much energy as welding. And even with induction flame brazing, the deformation are smaller than during the welding processes. And the last economic aspect is process tooling, assembly tooling. Welding requires much more complex equipment. Alignment of the parts to avoid offset after welding is required. It is also necessary to supply inner gas, for example, argon, from the root side of the weld to prevent material against oxidation. So this equipment is very complicated. In case of brazing, sometimes only spot welding on small ball tack welding is enough to keep position during the brazing. So there is no issue, which is better. The issue is application we have for that particular joint we do.
When you explained, I was just wondering if we are in a correct place, because our seminar is dedicated to the heat treatment. And we try to discover secrets of heat treatment technology, and we speak about brazing, which is very much connected to welding. And you represent a person who work in the department of heat treatment and brazing. So this is sometimes...
Yes. In our factory, we do only furnace brazing. So if the furnace means that the people who are responsible for heat treatment are dedicated for that process. So the welding engineers are a separate group, and the brazing and heat treatment engineers are my group.
Exactly.
So I am responsible for both, for heat treatment and for brazing.
But this is fact, in many companies I see the brazing, it's included in general heat treatment departments or something like this. If our attendees agree, please comment or tap on the chat. We are really interested on your opinion about this aspect. And just before, Irena, thank you very much for this explanation.
Thank you.
It was really nice. And just before this discussion panel, I received a question, again, maybe not the first time, but the question about the possibility of mixing different brazing processes in the same furnace. For example, having some heat exchangers brazed by copper, and if it's possible to do brazing of heat exchangers brazed by nickel in the same equipment, or even more sophisticated or more, let's say, strange requirement to use the same furnace for stainless steel brazing and aluminium brazing. And if you can say, Adam, maybe you can say something about this aspect.
Yes. Yeah. So the answer is yes and no, because it depends. When we want to mix the parts that are made out of the same base material, what do you mean that we want to braze the stainless steel with the copper and the stainless steel with the nickel? The answer would be yes, you can mix that. However, after the process with the nickel, it would be good to make the burnout which is the process that it's just burning out the leftovers of the nickel to braze with the copper. And it depends on the nickel alloy, but one of the very most popular BNI2 has the lower melting point than the copper. And now, if you want to mix in the same furnace different base materials, for example, if you want to put into the furnace stainless steel and then aluminium, the aluminium would require a little bit different furnace because we have a totally different melting points of the base materials. The other thing is, if you would like to braze, for example, brass in vacuum furnace, it's the same. No, because you cannot braze the brass in the vacuum furnace due to the evaporation of the zinc. So you could create a couple of groups where you can mix and what you can mix, but all of that goes into the what kind of base materials you want to join, and a little bit less what kind of brazing alloys you are using to join it,
and do you
which
think,
are connected to the base materials.
Adam, do you think, because I have also some opposite experience when switching from one brazing alloy to another, but with longer time reserved for the cleaning and maintenance of the furnace, sometimes with the possibility to technically to remove the hot zone completely from the furnace and make a mechanical cleaning and more. But I have to disagree a little bit because sometimes it can be possible. It's just the question of the cost of the maintenance and cleaning operation between switching from one to another, but from the requirement of continuous production point of view, it's of course an unnecessary operation. Everyone would like to brazing one after another and have a flexible equipment to different technologies. Do you agree?
So as I said on the beginning, it is possible, but as you have said right now, sometimes from the economical standpoint of view, it doesn't make sense. Of course, it's better to have a dedicated vacuum furnace for one process, and then you are you don't have to make these burners and removing the unnecessary leftovers during the brazing. So,
okay.
The answer is it is possible, but it might be.
It depends.
Really good for you. It depends, exactly.
Adam, thank you so much. The next question we have.
May I have one additional remark?
Please do, Leszek. On condition it will be short.
This remark is not really about the furnaces, but about the process. If you braze aluminium and copper, and in the same factory you have production in copper and brass, make sure that never copper gets into the production hall of aluminium. I've seen cases where there was an operator with gloves contaminated with some copper chips, and he was sent to assemble aluminium parts. And then all of a sudden the aluminium parts were burned through. They had very tiny holes caused by copper chips which was left on the aluminium part. Because copper will dissolve aluminium during the process of brazing of aluminium. So please make sure that when you have in one factory two productions, copper and aluminium, they must be totally separated one from each other.
Yes, it's a good point. It's a good point to remember to not only wash our hands properly, but to have a clean parts and environment in the factory when doing brazing different metals and different brazing alloys. Okay, so the next question. Thank you, Leszek. And the next question is about the most critical brazing aspects. So, Leszek, if you started already, please continue, and if you can explain us this, please do.
Well, basically, I must say at the beginning that my experience is connected with brazing of aluminium. But nevertheless, I distinguish 5 major factors for brazings: temperature, flux load and its uniformity, furnace atmosphere, joint geometry, and cleanliness. When we talk about temperature, I would like to show you a few examples what's going to happen when we have temperature which is too high. This is a radiator, a car radiator, and you can see that there is a line on the tube caused by flowing filler alloy towards the fin. And that flowing filler alloy dissolved the material of the tube and created a hole in the tube, a total reject. Mm-hmm. And such things can be caused by high temperature, also by temperature gradient between the first fin and the manifold, but also it could be the so-called fault die line on a multi-port extrusion tube. Another example of the temperature problem is connected with the so-called erosion. During brazing, when we have a liquid filler alloy, this, as I already mentioned, the liquid filler alloy can interact with the base metal. And sometimes upon cooling, the filler metal at the end flows away, leaving the base metal having much thinner gauge. This is asking for problems because such a part will not have the sufficient strength, and it will be also susceptible to corrosion because of the thinner gauge. So the point is try to avoid brazing at too high temperature.
So temperature control is
always a temperature which allows for the filler alloy to be molten, but the base metal should be always solid. Mm-hmm. And the next point is flux load and its uniformity. Flux, as I've mentioned at the beginning of my speech here, is needed for cleaning the surface. Every surface, metal surface, is coated with oxide, and that oxide must be removed in order to create that metallurgical bond between the filler alloy and the base metal. And fluxing is a separate, actually, field, and it's a very important process. But one thing is the key. Flux should be distributed on the surface uniformly and with required load.
And according to flux, it's do I have a correct understanding? It's mostly reserved for aluminium brazing, yes?
Yes, but also for cupro braze you need flux, right?
Yes.
The next factor is furnace atmosphere. Again, I'm talking about furnace brazing, and here we can have either vacuum furnaces or continuous furnaces. With continuous furnaces, we have the end of the muffles, which could be as much as 20 meters long, open. And we pump inside an inner gas. And the flow of that inner gas decides about content of oxygen inside the brazing zone. When something is wrong with the distribution of the gas, the furnace atmosphere is bad and we have no braze, or the parts looks not very nice. The fourth factor is joint geometry.
By the way, Leszek, if I can interrupt you, from the furnace point of view, according to our experience as a Sikoworwi experience, there are different type of furnaces. From the first time, they looks completely different, but also dedicated for brazing. So comparing the aluminium brazing furnace to the, for example, to small laboratory furnace, there are two different type of equipment, but still dedicated to brazing. And why I'm telling this, why I'm saying this, it's unbelievable for me how the creativity of the people is for the brazing. Yes, even from the historical point of view, where in ancient time people also made the brazing, yes, joints in completely different method.
Basically, the goal is the same. For at least for aluminium brazing, but not only, we need to have an atmosphere which is oxygen free.
Yes. And you mentioned something about joint geometry. So
right.
I interrupted you, and please continue.
Next parameter, which can be very complicated, but there is one general rule about the joint geometry, which is that there must be at least one point of physical contact between surfaces to be brazed. Or speaking colloquially, a filler alloy can flow on the surface, but it cannot jump. So somewhere a designer must make sure that in some point of the joint length, there must be a direct physical contact between two brazed parts. Another important factor for the designers is the so-called competing joints. A capillary force is a function of the gap between the parts, but also of the angle, which is shown here in this drawing. Actually, this is not the slide I want now.
Sorry.
Okay, this is the one below. A more open angle will create a smaller force to pull the metal into the end of the joint. And such situation shows that we have the so-called competing joints. Filler alloy will tend to flow to the right and not to the left. It's also very important when you design the parts. Please, next slide. Okay, here we have an example of filler alloy trap. Filler alloy trap is a place where we have a preferential clad flow, and due to that preferential clad flow, we can reduce the amount of available clad in the joint. A typical example, or a very common example of such a case, is a radiator, car radiator with the so-called B-type tube, where the tube is folded into such a shape where we have a small delta region where the filler alloy, from that place, the filler alloy is drawn into the gaps in between the tube and header and between the tube legs. And if we do not keep this open area, this delta region, small, we will end up with a fault as it is shown here on the microscopic picture on the right. Another example of a filler alloy trap we have here below, where we have a round tube with a round connector. And in this case, we created a filler alloy trap, right angle, which is shown here by the blue arrows. And we obtain possible leaks in the middle of the joint, because most of the filler alloy flows into the corner between the collar of the tube and the round manifold. It's a typical example for cost-saving design done by an engineer who doesn't know much about brazing, which result in increased rejects level.
This is true. It's many times it's difference between the, let's say, economical and the proper design.
Yes.
These two aspects.
Exactly. And the last factor I would like to say is cleanliness. Simply, the parts for brazing must be cleaned. They cannot have oil deposit on the surface, because if we have oil or other grease deposit or ordinary dirt, it will burn during the heating cycle and it will leave a nasty looking brownish or dark deposit on the surface. That itself would be something we could live with, but a dirty surface will not braze. And this picture here shows such an example where the manifold was not cleaned from oil, and the oil created a thin film of carbon upon heating, which could not have been removed by flux, and therefore there was no interaction between the filler alloy and the base metal, and that resulted in lack of lack of braze.
So it's not only the visual aspect, but also the proper brazing effect at the end.
Of course, very important. And in the last slide, as a summary, I would like to show you an importance of those factors. And here there is some kind of a practical paradox, because when we look at the brazing process, continuous brazing process, the last element we have in our process is the furnace. And after the furnace, the part is tested for tightness. Is it leak-free or not? And we discover that it is not. So the first natural question would be, do we have the temperature in the furnace right? And this is a wrong question. Because when we look at this slide, and this is based on my many years experience and analyzing statistically data, the major source of the brazing faults is in assembling process. Gap size mainly, fitting tolerances. Then cleanliness. Quite often the parts are not perfectly clean in real life. The next factor, furnace atmosphere. Well, we usually have a proper monitoring of oxygen and dew point. And when we have the right level of oxygen, again, this is the value for aluminium brazing, we will have no problem. Then flux level, the next factor. Sometimes we can have sporadic mistakes due to the nozzle clogging or other problems with application of flux. However, such problems are usually easy to discover. And the temperature is the factor which is the least frequent root cause of the fault. That's simply because the furnace temperature setting reliability is high. That's my opinion about Secowork. Usually, but usually it is the first parameter which is checked. So remember, assembling process is the most important one when you braze different parts.
It's interesting, and it's I think it's great to see the importance factors from the most important to the last. But in my opinion, it's also the complexity of this process. So the complex is important.
Perhaps actually saying importance is not really proper. It's the frequency of root causes.
Yes, yes. Leszek, thank you so much. And you mentioned about the temperature control, and in heat treatment and brazing, there is another factor. It's temperature and time. today I'm responsible also for the time keeping, so I have to switch to the next question. Thank you for the answer. And the next question, which is about what are the criteria and approval methods of brazing joints? Because it's, of course, important to know how to make the brazing, but it's also important to know how to check and verify if we made correct or wrong process. So now I give the voice to Adam. Adam, please share your experience about this.
Okay, so this is again very open question in terms of brazing, because brazing is very, as you could see, versatile and broad technology. But before we start talking about the criteria, I would like to start talking about the imperfections that we'll see, because then we can set up some kind of criteria against these imperfections, and we can divide imperfections for external and internal. By external, I mean everything that you can see by your naked eye, that it's outside on the joint, on the base material. And internal is what we have inside the joint, like when we're making the cross-section or peel-off tests, we could see kind of what's inside and what kind of imperfections will face it. So I put it on the slide, couple of common imperfections that we could see during the brazing. And for external, it's discoloration, incomplete fillet, cracks, and localized melting. And it depends what kind of products we want to make. For example, many industrial products are made that we don't, the discoloration is not a problem. Because it's just the discoloration and its physical appearance that it shouldn't be a problem in some of the industrial applications. But when we're making products that are that should look good, this discoloration will be a huge problem, and the criteria would be no-go, that we cannot accept this this type of imperfection. Cracks, obviously, most of the times no cracks are allowed, but there are still certain couple of cases where we could accept the cracks, but that's not very popular. Localized melting, in most time it's no-go, that we just melted base material, and as Leszek mentioned, we could see this erosion, which is kind of localized melting. And yeah, that's the imperfection. So it depends what kind of products we want to produce and what the customer will be willing to accept. That's the other thing. For internal imperfections, it's you can set up some kind of, you can set up the goals for it. For filling imperfections, for example, one of the most, maybe not a famous, but the most common criteria is that we are allowing 20% of the joint to have the imperfection. So for example, if we cut up the joint and we see some imperfections, the area filled by the filler metal should be more than 80%. That's, and you could go deeper into that and see what's the type of the joint, if it's overlap joint, what kind of overlap we have, if it's 3 times the thickness, 6 times the thickness, and set up the criteria against that, and what's the strength we require. Lack of fusion, obviously, it shouldn't be go, because if you have the oxides on the surface, as Leszek mentioned, we might see lack of fusion, because there is no, the braze alloy won't spread on the surface, and there is no stickiness. Cracks, obviously, that's not go, and erosion, it depends. In erosion, you might see some erosion that it's not a big deal, or sometimes the erosion / diffusion. It's used as a joining technique. That we heating up so long that we eroding the base material that it's mixing with the braze alloy, creating a very strong joint. But that's a different. We could say that's a diffusion brazing. Yeah, and
Adam,
what are the approval methods?
If I may interrupt you just for a moment, I remember our preparation for today discussion panel, and when we discussed with Irena, she mentioned that it's according to verification and approval methods, it's always good to know, to have behind that we are trying to find the correctness of the brazing joints, to find the good aspects and to approve the parts to the production. Because if we try to find some incorrections, it's only the matter of the method we will use. What do you think,
Yes.
Irena? Am I right? Do you remember this discussion?
Exactly, Adam. Yes, I confirm. We can use a very complicated, the new, maybe not very new, but expensive method, which is tomography. If you want to find something in the joint, for sure, using tomography, you can do that. So how to do correct parts if we use too complicated, too sensitive method for inspection? Is always the question how to do that. Where is the border between good quality and some imperfection which we can approve?
Yes, it's like with us. Nobody is perfect. If we go to a doctor,
Exactly.
they will find something. Sorry, Adam.
Exactly, it's exactly the same.
Adam, if you can continue. Sorry for this interruption, but please continue.
No, this is pretty good. Yeah, that's why we should think about the criteria as our go-no barrier. What's the border? Then you just defining the criteria that it's connected to the reality and the joint function, not that the criteria have to be very strict because it should be strict.
Yes.
So, and as Irena mentioned, you could, I want to position myself in the camera. As Irena mentioned, you always find something in the brace joint. That's how the brace joint is working.
Okay.
And you could use different methods: visual inspection, checking it outside, metallographic cutting and seeing what's inside, and radiographic, which is most sensitive and most expensive, will show you everything. And one of the simplest criterion is that you checking the joint from both sides. If you're applying the braze material from one side, and it should flow through the joint on the other side, and you see the flow on the other side, it means at least in 50% of the cases that it went okay.
It works.
Maybe not good. When you cut it up, you might see a lot of defects inside, but you are on a good track with that. And for some of the applications, that's it. That's enough. For other more critical applications, we should perform metallographic inspection of the leak tightness, and radiographic should be used as a rather failure analysis because, yeah.
Adam, thank you so much. It was a great explanation to me. And let's go, if I remember, to the last question, which is about experience with staff training and their qualification. And as we can imagine, it's not so easy to have, you mentioned about the torch, for example, brazing, where the manual work is not easy to make in a repeatable way. And the same is about the control and verification and experience of staff. So Irena, how is your point of view on this aspect?
It's the main point of view is very easy. The quality of brazing joint strongly depends on the skills of the personnel who is doing these operations. Not only brazing operation, but all of the activities we need to design and to perform good joints. So assembling, cleaning, everything. The personnel who doing this process must know all these rules. And I would say that it is difficult to make good brazed joint and qualify it as per Adam before slides if our staff is unskilled. Each department of industry has its own requirements regarding the method of qualification, the frequency of the training and exams which we conduct for operators and for, I would say, for personnel, maybe not for operators, because personnel we can divide by two definitions. The first is brazier performance. So brazier performance qualification tests determine the ability of brazier to make sound brazed joints following a brazing procedure specification, the technology, written technology, and under conditions that will be encountered in production application. So the brazier means all people doing assembling, taking care about the clearance and applying brazing filler metal like foil or paste. And the second group is brazing operator. Brazing operator performance qualification tests determine the ability of brazing operators to operate furnace, mechanized or automatic brazing equipment in accordance with written procedure. There is a very detailed specification, AWS, American Welding Society, B2.2 specification, which very clearly define how to qualify joints and process and how to qualify the staff. And I would say that brazing performance qualification may be done in two ways. The first is similar as Adam said, visual examination. So we have to check evidence of brazing filler metal, brazing line, presence of unmelted brazing filler metal, undercutting, cracks, erosion, etc. The second, more detailed, is qualification by specimen testing. So visual examination plus macro test of the samples and peel test. Peel test we use to evaluate the coverage, the filling of the joint. So this test will show also internal discontinuity, internal voids, pores, crack, inclusions, and level of coverage. But although we qualify the joint, qualify the personnel, there is another variables, various combination of components affecting the quality of the joint. So the requalification is required for brazing operators. So means that the furnace brazing operators or mechanized equipment operators, if any changes from one brazing process to another is done. For example, if we do previous qualification using oxyacetylene torch, and now we do resistant brazing process, we have to requalify the personnel. If we discuss about the requalification for brazers, the variables for that, the first issue is also brazing process. So any changes from one brazing process to another must be repeated requalification. The second issue is base metal. Before the joint was steel, now we change it for nickel alloys. So requalification is needed. The third issue is brazing filler metal. Different skills are needed for nickel brazing, different for copper, for silver, etc. The flow, the capillary action occur a little bit differently, so the personnel must be requalified. And what is very important is the joint design, the brazing position and flow direction. Next slide, please. We can specify 4 main group of flow direction. The pictures here show you these details. The flow direction is especially critical when we do manual brazing with fuel, with torr brazing. So as you see, there is this is an example of the standard of the specification that define very precisely how to qualify joint and personnel. The qualification is very important to avoid poor quality costs.
Irena, thank you so much.
But for sure, in the market you can meet also another specification, not only American Welding Society specification. But this is, I would say, the most popular in the aviation industry.
Yes, I wanted to say that it's always interesting to me to know your point of view from the aviation perspective, where not only equipment has to be qualified, but also the skills of operators and generally staff has to be qualified too.
I would say also that although the variables, the joint is not changed, we have to repeat periodically the training of the personnel and the exams. So every year they are trained and examined.
This is true. Many times I say that it's not only the equipment is important, because we go to the modern world of also artificial intelligence, but also the intelligent operator is not less important than the good equipment we have for brazing. Irena, thank you very much. And we came to the end of our discussion. First of all, thank you so much for our discussion today. And I can say that you are not only the practitioner, but you are a true expert to me that I can count on. So thank you so much. And also big thank you to all the participants from the other side of our streaming. It was, believe me, it was a little bit crazy experience to all of us, but I think we all now are partially in a virtual world. It's our, let's say, new normal. So thank you so much for participating. I will be happy, and my partners from discussion will be happy to see some comments on the chat. And for the end, my conclusion is the question: what interesting did you learn from true experts today? If you can tap on the chat, it will be a pleasure for us to see. And in this way, I say thank you so much for joining our virtual e-seminar of Sika Warwick, and hope to see you somewhere in the real world or in the virtual way. Thank you very much. Bye-bye.